My name is Mark Fickett. I'm from Form Energy in Boston. Today I'm talking about quality in data pipeline software. I think structured logs in particular are a key tool for reliable data pipelines, and one that's not frequently used in or really designed for this domain. So I'm going to start broad and narrow in. How is Form Energy working on climate change? What do we need software for at Form? What's our stack? And finally, what are some examples of problems we've solved with this one particular tool around data quality, structured event logs? So what's Form doing? As the world transforms to a more renewable grid, the viability of wind and solar production becomes an increasing problem, or the variability rather. Often an argument against feasibility of renewables is implicitly about grid storage. Where do we put excess energy? And then how do we provide energy when it's cloudy or still? There are existing solutions, but nothing that works quite right or is cost competitive with fossil fuel plants. The status quo is usually coal or natural gas peaker plants that can respond very quickly to demand changes, unlike nuclear, for example. So what's hard about grid storage? What's the competition? One existing storage method is pumped hydroelectric. When power is needed, gravity drives water through a turbine. And then when excess electricity is on the grid, we pump water back up from a low reservoir up to a high one. And although that has around 80% round trip efficiency, there are a few locations for it, and it costs a lot to build. And you're probably more familiar with lithium ion batteries. They're more flexible, and they have even higher round trip efficiency, about 95%, but they're expensive. And they're typically used to provide grid backup power for about 8 hours, which they do very well. But increasing battery capacity to cover the standard long duration of 100 hours would simply cost too much. So there's the gap: long duration storage at low cost. I joined Form in 2021, looking for a way I could apply software to climate change. Form's developing iron air batteries, which address the long duration storage problem. And luckily for me, Form uses software in a couple ways. First, Form needed to find the market requirements. What's the price per kilowatt, the duration, round trip efficiency, and so on that would make these new batteries hit the utility requirements, so the utilities would prefer them to existing options. And this involves simulating energy costs and consumption that vary by location and over time, and not just for 24 hours, which is typical of the energy sector, but over a full year, since weather and demand change a lot. Just for one key insight, with cheap enough materials and fabrication, a relatively low round trip efficiency is still economic to serve the grid's needs. Might not be what you expect looking for grid storage batteries. So the first software product identified the goals, and then Form embarked on running thousands of experiments, each lasting weeks to months, to simulate the long charge and discharge cycles of these batteries. And that brings us to the data pipeline group at Form. That's where I work. I think our pipeline is actually pretty typical in some ways. We start with messy, complex data, and we make it nice for analysis. Here's what that means at Form, though. Battery development companies, including us, rely on commercial battery cyclers to drive experiments. So these are refrigerator-sized power supplies. They charge and discharge new kinds of battery cells and record voltage, current, reference electrodes, whatever. And they're all similar in spirit, but cyclers from different manufacturers, of course, keep data in slightly different formats. And worse, a lot of them like to use their own local databases. So individual battery cells, when they're on these, they also need to be moved around temporarily, maybe put on a shelf for a while. So their database rows are split up. Then on the output side, analysis, going through the results of an experiment, often need similar computation. So for example, most experiments want to compare the charge and discharge round trip efficiency on the first cycle to the 5th cycle. So we compute standard summary metrics or aggregations. And then the hard part, which is why I want to talk about it, is that this needs to work reliably across thousands of experiments and deliver fresh, correct data each morning. And the requirements are probably going to be different next quarter. So let's talk quality. I spent most of my career as a full stack software engineer at Google. I got 9 years of experience hands-on running software running at global scale, distributed across servers, written in different languages. And a consistent feature across different teams and projects was what makes quality. What makes it not just possible, but really second nature among these teams to keep a complex changing software system running. And issues of meeting user needs or projects getting canceled aside, Google's pretty good at that. So when I joined Form, the pipeline was processing significant data, but I could see gaps. We didn't have the quality essentials. The pipeline ran on a single Mac Mini, and the team members had to remote desktop in to do maintenance, open log files, reconfigure how the pipeline was started, all that kind of stuff. Most logs were gathered in Grafana, which is good, but there was a long list of manual checks about looking through the logs before and after each release for QA. And we had some automated alerts, but they depended on LogQL, which if you have used Grafana with Loki is a pretty arcane query language. And we had regular expressions in LogQL, pulling details out of log strings. We did have an important starting point though, which was the code base was clearly structured. We had separate subpackages addressing different steps of data processing. And we separated concerns like the multiprocessing stuff, database interaction, core business logic. And there were also pretty thorough unit tests. So we could make necessary changes and have confidence that things would keep working. That's the problem. There was a quality gap, but what was the target? There are well-defined best practices for running production web app microservices, but that's not really true for data engineering. My challenge working with the growing pipeline team was to apply the patterns that I was familiar with from Google, but pick out new tools in this new domain and plug them together in kind of new ways. Here's our stack and the different way components contribute to quality. Dagster does application orchestration that offloads the logic of evaluating a complicated set of data dependencies using multiple threads. And it helps us run the same pipeline locally for development and in the cloud. And as a third-party tool, it has active developer support and clear documentation and provides APIs, which all make it good to integrate into this quality paradigm. Circle CI runs unit tests, functional tests, regression. You're probably familiar with continuous integration, vetting every commit with some automated tests before you get to a release, and there's some surprise. One really useful pattern we set up is regression tests that run a representative portion of our production data. So we take a few experiments, which are selected by developers to exercise different types of processing, and then we run those through a full pipeline in a containerized fresh database. We do that first from scratch and then in a simulated incremental processing. That's been really key to finding errors that arise from data variability. We use AWS for our cloud execution. That's on EKS, their managed Kubernetes service. And containerized execution versus on-prem gives us a repeatable production deployment and easy hardware scaling. And for example, one initial scaling concern was just how much hardware can we fit, not really on a Mac Mini, but any single box we put in our lab, we can scale up a lot further with AWS. It's not all rosy though. We've had challenges with Kubernetes, like RAM management in particular, and just scaling our overall pod count. We use infrastructure as code like Pulumi to configure our cloud services. This means everything from various credentials our applications need in AWS parameter store to Kubernetes node launch configurations and IAM policies, even to our production monitoring boards and alerts in Honeycomb. That all goes through code review, version control. And to call out one kind of less obvious way that is really great We've run into cases already where something in AWS gets weirdly broken in some way. And rather than trying to debug it in place, we just destroy the resources and let infrastructure as code chug away for 10 or 20 minutes and recreate everything. And then it's in a known functional state again. And then logging. The standard Python logging framework integrates log streams from the orchestration framework from Dagster and from our application logic. Great to use, good standard tools. And then log handlers write the console logs as well as machine readable JSON logs that get picked up into Grafana by Fluentd. But our observability also includes what I'm really excited to talk about, structured events and tracing. You need to know what your code is doing. And the de facto standard is writing log messages to standard error or gathered up by Fluentd and sent to Grafana, but text logs. And with distributed execution of a daily pipeline that runs for 4 or 5 hours, processing thousands of experiments data, you need some kind of aggregate view. You can't just page through or even search through text logs. So to monitor our production pipeline, we publish structured events using OpenTelemetry. And then we use Honeycomb, which is a SaaS observability platform similar to Datadog, to aggregate, view, and alert based on those events. We can understand our data pipeline's performance at large in summary, and we can focus in and debug errors quickly when they occur. Here are some examples to show how we use observability to get back to that goal of delivering high quality data reliably. One of our most common concerns is missing data. Analysts go to review their experiment and the data is missing or not up to date. To track whether and what data we're reading into the pipeline from cyclers, we can publish an event like this. We've got a count of new rows. Some tasks just process these rows pulling out of the cycler database. And we have the brand of the cycler it came from here, a maker. By gathering events like this, for every one of the 1,000 experiments we process, we can essentially run SQL on our debug logs, which is super fun. The chart on the right is how many new sample rows did we get each day over the last week, broken down by the cycler brand. So continuing the example, our maker cyclers depend on an intermediate cron job to get data over to the pipeline. And one time we were debugging user-reported errors and we discovered the cron job had failed to run a few times. Obviously not the way you want to find out about errors. So now with structured events, we get a proactive alert if the daily new rows by cycler type drops to 0. So we know here in this chart, you can see the green line dropping down to 0. Our makers stopped bringing in data. Our on-call follows up with the appropriate team and the issue is fixed, usually before anyone misses the data. This chart is before we had that alert, so it's stuck at 0 for a while. There are other advantages to structured events too. Since you're querying data, you can worry much less about log volume and include lots of potentially interesting attributes, kind of similar to filtering log levels, but more flexible. So proactively adding events with many attributes can come in handy when you're planning new features or debugging unexpected issues. And it doesn't obscure dev logs like lots of debug statements might. So example 2, why is our API call getting flaky? As a precaution and just kind of a good practice, we wrote our API client to publish events with call latency. And what we see here is it's creeping up to 30 seconds. It turned out there was a processing timeout on the remote server, actually an AWS Lambda gateway. And looking at the latency events not only showed us that we were getting close to that 30-second limit, but also gave us a pretty clear trend. So we could see how many software development sprints do we have before all our requests start timing out. Again, we've got a nice 2-month trend line of API call latency, which would be really hard to extract from text-based logs. So events are great, but observability has grown up around microservice web apps, not data pipelines. Let's look at one feature of OpenTelemetry, the backend tracing SDK that puts all this data out. It helps with tracing for performance analysis. And here's a screenshot of Honeycomb where we use it. This is a flame graph of a small testing pipeline run showing the relative durations of different portions of the pipeline. Some of them are running in parallel. In a web app, one trace like this typically covers one user-facing request. So you get a click, you make an XHR to the back end, query the database, deliver and render the results. And all those different steps happen on different servers, but common services like React or Flask have built-in support for passing along headers with a trace context. So your observability platform can stitch together a comprehensive view like this end to end, and then you can identify performance bottlenecks or problems in your data that result in errors way downstream, even between services. The Dagster, our orchestration platform, doesn't have OpenTelemetry integration yet. Neither do other popular frameworks like Airflow or Prefect. Each execution step happens in its own context, and that might be a Python subprocess in local development or a Kubernetes pod when deployed. And also it can be, separately, it can be useful to set attributes on a parent span. A span is each one of these lines, usually a Python method call, and have those attributes automatically picked up by a child. Here's another flame graph, similar idea. The purple circles are portions executed by different Kubernetes pods. By stitching those together, we can see quickly, for example, at the bottom, 30 exceptions from pods doing data heavy lifting all get thrown, but we can connect them back to the pod at the top where some common parameter is getting loaded that determines how they're going to run. We can make that connection because we're propagating the context between those pods. They're not isolated. And then the light blue underline is a span attribute. It might be set on a parent and then propagated to a child. That means when in the child, the database write fails with a foreign key error, down at the leaf of the call stack, it already has the experiment ID that we'll need for reproducing the error, even though we only made the effort to set that as a span attribute a few layers up in the call stack. We don't have to put the same attributes into every log call. So contrast that with text logs, where you might need to pour over a bunch of interleaved logs from different parallel workers, or maybe you kept your log messages short so the experiment ID isn't in the exception message. And to get to real debugging, you might have to go back, modify some log messages, push a new release or a hotfix, and wait for the error to recur. Using events just makes our lives a lot easier. And quick plug, we open sourced a library to solve these particular problems of adapting events to data pipelines. Does two things. It adapts trace context propagation for Dagster. That's the part about connecting your work in different Kubernetes pods. And it might even, if you're using a different framework, it's pretty simple, but it might serve as an example. And it also adds attribute inheritance, which is not specifically tied to Dagster. So you can set attributes on a context manager, and then every contained span or event picks up those same attributes. Now let's walk back up the stack. Why is this necessary? Starting at the bottom, structured events attach the right context to errors. With some custom glue, that work, even within the data pipeline domain, gives you events that let you find errors more quickly. And they include the information that we need to fix errors immediately. Or sometimes there are no errors, and you can say that confidently. Having a flexible expressive orchestration framework gets us reliable and efficient code execution on different compute environments. So our dev matches our prod execution, even though it's different compute. And cloud execution gives us reliable scale and security, or probably better security than dealing with OS updates and antivirus stuff locally. add infrastructure as code, and we have clarity around our resources, disaster recovery, and we can deploy smoothly across multiple environments, different cloud services. And with quality software, which is really more of a process than some boxed up solution, we deliver our data. We deliver it to the teams who depend on it for their decisions. And we can have confidence that it's correct and we'll have the data when they need it. Concretely, at Form Energy, we're using the pipeline's output. We can hopefully make something impactful. We can create multi-day storage batteries that will fit utilities' needs to fight climate change. Thanks, everyone. I'd love to hear questions and any different ways that you address data quality or challenges you're facing with data pipelines.